Okay, first chapter on thermochemistry, which is just kind of roughly, loosely energy chemistry. So we're going to be focusing on energy primarily and how it relates to chemistry. So one great example of thermochemistry is chemical hand warmers. So the little like hot hand pack things where you open up the thing and then it's a little, not really squishy pack. You shake it and it gets hot and then you stick it in your pockets or whatever. Most of those types of hand warmers work by using just little iron shavings that react with oxygen in the air and form rust. So you shouldn't eat those hand warmers. I mean, for a bunch of reasons, but one of them, you just shouldn't eat rust. It's bad for you. And the amount that the hand temperature or those hand warmer temperature is going to rise depends on a couple of things. The size of the hand warmers, and if you're sticking them into your gloves, you know, the size of your gloves, how big your gloves are, the amount of insulation in your gloves, and also the amount of thermal energy that's released by the reaction. Our universe is composed of matter and energy. We've mostly been focusing on matter so far, so things that have mass and take up space. And we're going to be focusing more on energy, because energy is related to matter. So thermochemistry is our study of the relationship between chemistry, the chemistry part, and energy, the thermo just kind of referring generally to energy. Energy, you may know or remember, is the capacity to do work. Work being a force acting over a distance. Energy is also related to heat. So heat is the flow of energy, typically caused by a difference in temperature. And the flow of temperature is from hot to cold, or from high energy or high temperature to low temperature. Energy can be exchanged through contact, so directly touching something. It can also be transferred indirectly, like as energy waves, so like infrared heat can also transfer energy or transfer heat. Energy is a quantity that we possess, that objects can possess. So we can think of, there's going to be a bunch of analogies with billiard balls, pool, or snooker, depending on what you play. But the balls, the billiards balls, can roll. So in frame A, we've got a ball that's rolling because it's got some motion. Maybe it's been hit by the cue, or it's been hit by the stick. I think that's a cue. So you hit the ball and it starts rolling because we've given it energy, and it's going to just keep rolling until it hits something else, and then it converts that energy into work. It does work on the other ball, the purple ball in this case. It transfers energy and ideally either stops or it would maybe bounce back a little bit. And then if the energy is completely transferred, then this purple ball now has all the energy and it's going to roll. So heat and work are ways that we can exchange energy. This white ball has energy. It collides with the purple ball and it does work. It acts on another object, transfers its energy to the purple ball. So energy can move both out of or into an object. And we've got a couple types of energy. So one of our main types of energy is kinetic energy. Kinetic energy is motion energy. For once in my career, I'm sitting on a stool rather than a chair with wheels when we're talking about energy. So normally I would just like roll across the class to show you kinetic energy, but like walking would also work. Students got it? Yeah, rolling around is kinetic energy, driving kinetic energy. A type of kinetic energy, or a type of, kinetic energy is thermal energy. Thermal energy is temperature energy or heat what we might think of as heat energy, but we're defining heat as the transfer of energy. So thermal is temperature energy. So lots of thermal energy, high temperature, not very much thermal energy, low temperature. Thermal energy is a form of kinetic energy because it's the molecules, the atoms, the particles vibrating, moving around. And the more that they're moving, the higher the temperature, the more that they're moving. We've also got potential energy, and there's a couple types of potential energy. Potential energy you can sort of just think of as stored energy or saved up energy. So it's usually related to composition or it's related to position. One of the big examples, the common examples of potential energy is gravitational potential energy. So when you lift something to greater and greater heights, you've imbued it with some energy. If you let go of it, then it will fall because of gravity. So that would be an example of one form of potential energy. There's also chemical energy, which is potential energy stored within bonds, and it's just all stuff related to atoms and molecules. So chemical energy is stored in mostly bonds. So the way that atoms are arranged relative to each other, the relationship that they have to each other. So an example of chemical energy is like all explosives. If you give them a little spark, or sometimes if you just touch them hard enough, or if they're just out in the air, the way that they're arranged, they really don't like to be arranged that way. They're kind of, we can think of it as being all bent up, like if you think of like a spring or a piece of wire, it's all bent up and compressed. And if you give it a little bit of a spark, then it breaks all of those bonds, shatters into a bunch of different pieces, and releases a ton of energy when it does that. So energy is our capacity to do work. We can do that as kinetic energy, kinetic again being due to motion. Thermal energy can also is a type of energy. It's associated with temperature. And then for potential energy, this is all position or composition. Position, we usually think of gravitational potential energy. Related to position, like a ball will roll down a hill because of gravitational potential energy. And for chemical energy, we're thinking about like the shape of the chemical, the way that the bonds are structured, and things like that. Like with mass, we've got a law of conservation for energy. So the law of conservation of energy states that energy can be neither created nor destroyed. So if energy exists and it disappears, then it must have gone somewhere. It doesn't just vanish, poof, it's gone. So generally, our energy is just going to be transferred from one object to another. Sometimes we can sort of like hide it in the form of like chemical potential energy, or if you think of springs, if you like pull on a spring, there's some energy associated with stretching a spring or compressing a spring. So we can kind of store energy in that way. And here's an example of somebody dropping something, in case you wanted to see that. Gravitational potential energy, because the cue ball is above the table or the pool ball is above the table, you drop it and it falls. It converts that gravitational potential energy to kinetic energy and it falls until it hits something. Compressing a spring also works as a way of storing up potential energy, or stretching a rubber band would also work. When we talk about energy, typically we are going to be talking about two distinct things. We have a system, which is just kind of generally the thing that we care about. So the system is the area or the set of things or the specific thing that we care about. The thing that we are looking at, the thing that we are interested in the moment. So this room, our lab, we could think of as a system. We could think of a chemical reaction vessel as a system, like a beaker or an insulated cup. We could think of that as a system. So we would just be studying what's going on in this small area. We could expand our system out to include like the entire planet or a large building. It's kind of however you want to define it. It's but just generally the thing that we care about. And then everything else, everything that's around that, is the surroundings. So our surroundings is everything around the system, however we've defined the system. So if our system, if we're doing a heat transfer and we've got like a styrofoam cup, the styrofoam cup, we've probably got some water, there's maybe some metal in there, that would be our system. And then any heat loss that gets through the styrofoam cup would just be to the room, which would be considered surroundings. If the iron that's reacting in our hand warmer is our system, then the surroundings would be our hands, our gloves, the air in the glove, the air outside the glove, the rest of the known universe. But that's probably less important than the close things. So we'll usually just talk about system versus surroundings. Conservation of energy means that if energy is gained or lost by the system, the thing that we care about, then the surroundings must have an equal and opposite reaction. So energy lost by the system didn't poof, just go nowhere. It was gained by the surrounding. The surroundings is just kind of a catch-all for the other place. And so we've got an example of that with some gauges. So before an energy transfer occurs, we've got our system at what we're showing here is half energy. And then after an energy transfer, it's going down to 1/4 energy. Our surroundings started at 1/4 energy and went up to 1/2 energy. So we transferred this little bit, this little quarter tank of energy from our system to our surroundings. The total amount of energy is still 3 of these little bars, both before and after. So we haven't destroyed any energy, we've just shifted it around, we've just moved it from one place to another, from our system to our surroundings. We've got units for energy. Commonly we're going to see the joule, Joule, the joule as our unit of energy. We've seen joules a little bit before. We saw them briefly in the previous chapter, like right at the end. It was kind of like just a throwaway, here's what a joule equals so that you can calculate stuff. So kinetic energy is 1/2 mv squared. So the mass times the velocity squared gives you kinetic energy. And since mass can have units of kilograms and velocity has units of meters per second, 1 kilogram meter squared per second squared is what we would define as a joule. So we'll often see joules because it's our SI unit of energy. It's a small amount of energy. So oftentimes we'll also instead see kilojoules. Other forms of energy include the calorie and the kilowatt hour. The calorie and the calorie is kind of a frustratingly, why do we have 2 things that are called the same thing, but one of them's capital and one's lowercase? Historical reasons, I'm sure. So another unit of energy is our calorie, lowercase c calorie. And the shortened form is lowercase c cal. This is defined as the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. So somebody decided that that's what it was going to be way back in the day. And 1 cal, lowercase c cal, is 4.184 joules, and that's an exact conversion. We then have the modern, what we probably think of for calories, capital C calorie, which is the nutritional calorie, also sometimes called a kcal. And this is the calorie that's on like food nutrition facts. So if you're tracking your macros, or if you're, I'm trying to lose some weight, I'm trying to gain some weight, and you're thinking about your calories, these are the calories that you're thinking about. You're thinking of kcals or nutritional calories. So I think probably the most important part of this slide is just be aware that we've got a lowercase c calorie, and it's different from a capital C calorie. If you get them confused, things will end up being wrong in some way. So do not confuse your calories. Do not confuse cal and cal. We also have the kilowatt hour, and this is the one that would be used by PG&E or Southern California Edison or whatever your power company is for measuring the electricity on your bill. So that's the one that you pay, I don't remember how much it is, but it's like 30 cents a kilowatt hour or something, 70 cents. It's somewhere in there. This is the one that's on your power bill or on your power meter, probably at home. We've got conversion factors for units of energy. The converting is kind of all the same. And there's also some comparisons of what those units of energy are like. I think the conversion's probably simple enough that we're not going to touch them too much. So we also have thermodynamics. So dynamics, like motion. So thermodynamics is a study of energy, that's the thermo part, and the ways that it gets converted. We've got a couple of laws of thermodynamics. Our first law is that the total amount of energy in the universe is constant. So if we were to collect up all of the energy in the entire known universe, I think this is technically wrong, but we'll just pretend that it's true anyway. The total amount of energy is constant. I think it's changing a little bit, but it's not important to us. In our universe, in our the realm where we live and exist, it's going to be constant. So if you're creating energy, quote unquote creating energy, if you're generating energy, that energy had to have come from some other form of energy. It's like solar power turns the sunlight energy into electrical energy. Dams turn hydroelectric energy, the flow of water, into electrical energy. And we'll introduce state functions here. So a state function is a type of function that depends on the start and end values. It depends only on start and end. I'll call it values. So for example, change in altitude on a mountain would be an example of a state function. Regardless of where you start, you can take your final elevation minus your starting elevation, and that's your elevation change. It doesn't matter how long it took you to get there. It doesn't matter if you went up 5,000 feet, went down 4,000 feet, and went up another 5,000 feet. If you did that directly, instead of going up and down and up, your change in elevation would be the same. So it doesn't depend on the path. The distance that you walk or the distance that you travel may affect, how tired you are, how much energy you exerted, but it's not going to change the total amount of elevation that you gained. The opposite of a state function is a path function, so path functions depend on what path you take. Internal energy is E. It's the sum of energy in a system. So both the kinetic and potential energy in a system. And internal energy is a state function. So it doesn't matter how you spend or interconvert your energy. At the end of the day, it's just your final value minus your initial value. So it doesn't matter how you spend your energy, just how much you have at the end versus at the beginning. It's a little bit like money. Money is a pretty good analogy for energy. If I give you $50 and I say, go out, have a fun day, and bring me back at least $10 in change, you can go out and spend all $40, all at once, all $50, and then make back $10, busking on the sidewalk or something, or you just rob somebody. However you want to get those $10 back, as long as you bring me back $10, I won't be mad and I won't care how you spent it. You could spend, $2, play the lottery 20 times or whatever. All that matters is how much you were given initially and how much you come back with at the end. And we use this symbol delta to represent the change in. Which I think we've seen before. Okay, so for internal energy, in a chemical system, a reaction, a mixture of chemicals, the reactants constitute our initial state. So our reactants are the start, and the products constitute the final state. We're going from reactants to products, so this is our initial, and this would be our final. And we can draw energy diagrams showing how our energy changes. So for the reaction of carbon with oxygen gas to make CO2, our reactants would have high energy, and our CO2 is a relatively low energy chemical, and so our CO2 has lower overall energy. So this would be a negative change in energy. Our delta E, our change in energy, so our reactants minus our products. We can see that we went down on our one-axis graph. Going down would be a negative value, so we lost energy. Our system lost energy. Obviously, that energy didn't just poof disappear. It must have gone somewhere, and that somewhere that it went would have been into the surroundings. So our surroundings have a positive change in energy because our system has a negative change in energy. The energy went from our system into the surroundings. And we can talk about the energy of our system, the change in energy, SYS. We can talk about the change in energy of our surroundings with SURR. So in this example, since our energy changed from our reactants to our products, that's our system. Since that value went down, we lost energy in our system. So our change in energy for the system is negative because, again, energy goes down. The energy that's lost by the system has to be gained by the surroundings because of the law of conservation of energy. So the change in energy of our surroundings is positive. If we reverse the reaction, if we go from CO2 and hit that with our little atom smashing hammer, and we make carbon and oxygen gas, we've flipped our initial and our final state. And so the sign changes. So instead of being negative, our change in energy of the system is positive. So our change in energy for our system is now positive. We would have had to put energy in. CO2 is a relatively stable molecule, so you have to put energy in to break it to get back your carbon and your oxygen. So our reactant, our CO2, is the low energy state, and now we're going to the high energy state of our products. So our change in energy for our system is positive. That energy must have come from somewhere, and the place that it came from is our surroundings. And so the change in energy over the surroundings, maybe a hot plate, maybe an atom beam, something like that, our change in energy of our surroundings must be negative. We had to lose energy from our surroundings, from our hot plate, put it into our system, our chemical reaction. And this is just kind of a summary of the previous slides. If our reactants have a higher internal energy than the products, then, so if we have higher internal energy in our reactants than our products, then energy goes down, energy is lost by our system, energy is gained by the surroundings, because that's where the energy went. If our reactants have a low energy relative to the products, we have to put energy in. The change in energy of our system is positive. So those are the two options that we have. You could also probably retain the same amount of energy, but I don't think we're going to be really talking about those. Any questions about energy so far? Cool. All right, consider these fictitious internal energy gauges that describe the initial conditions for a chemical system and its surroundings. So initially, our chemical system has 3/4 of a tank of energy. Our surroundings have 1/4 of a tank of energy. Which of these energy gauges corresponds to the final conditions following an energy exchange in which the change in energy of our system is negative? It would be A. So A is the correct answer here, because our starting state, our system, starts at 3/4 of a tank. In A, it's gone down to 1/4 of a tank. Or sorry, half a tank. It's gone down 1/4 tank. And so we've got 1/4 of a tank of energy that's lost by the system, which is then gained by the surroundings. C, this option over on the right, our chemical system has gained energy, and that would be a positive. Delta E for our system, because our system has gained energy from the surroundings. And then B is just impossible. We've done a no-no in B because energy was destroyed. If our system lost some energy, it must have gone into our surroundings. And the way that we've got it drawn out in B, it didn't go anywhere, and energy doesn't mystically, magically disappear. So the correct answer is A. Okay, so we also have some specific ways that energy can be transferred. They can be transferred as heat. Think like hot stuff to cold stuff. Transfer of energy like that. We can also transfer energy as work. Q and W are not state functions. So that would make them path functions. So their values depend on the process that you use to get to the final state. Our change in energy for our system or our surroundings is going to be Q plus W, so our heat plus our work. So heat we can think of as movement of thermal energy. For work, think more like pushing stuff around, picking stuff up, setting stuff down, like physically moving of objects. And an example of this, we've got our pool table back again. So we've got our white ball, our cue ball, that is imparted with an initial kinetic energy of 5 joules. So it's hit by the cue, and it's on a path to collide with our purple ball. The heat that it loses is 0.5 joules. Let's just say that it's lost from friction with the felt of the table. So it loses a little bit of energy due to friction. It collides with the purple ball. It's got 4.5 joules, and it imparts the rest of that to the other ball. So our purple ball gains 4.5 joules of energy as work. The total change in energy, we started with 5 joules, we used up all of our joules, all of our energy. So when our ball is sitting here at rest, it no longer has any energy, no longer has kinetic energy at least. It lost all of its energy to the surroundings, either as heat or as work. If we had a really rough table, like we bought a cheap pool table, or it's just badly in need of retrofitting, refitting, repair, we could maybe lose 3 joules as heat due to friction. And then when the ball runs into the purple ball, the white ball runs into the purple ball, we've only got 2 joules left, even though we imparted it with the same 5 joules. Only 2 joules left to go into our purple ball. And so our change in energy of the system, we still went from 5 joules to 0 joules, just sitting at rest on the table. But the path that our energy was lost as heat or by work, the kinetic energy imparted in the collision, were different. It had the same kind of general final outcome. We lost all 5 joules. And so for our delta E, it was the initial value minus the amount that we lost. The change in energy, 5 minus 0 minus 5. Because it's final minus initial. So our change in energy for our cue ball, our white ball, was that we lost 5 joules. But we saw in both of our scenarios, we had different ways that we lost the energy. So the Q value, the heat value, and the work values were different for both cases. For scenario 1, Q, the energy loss as heat, was negative 0.5 joules. For 2, Q, the energy loss as heat, was 3 joules. So they were different values, and our work was a value that complemented that, so that we lost all 5 joules. Okay, let's say that we've got a cylinder and piston assembly. That's our system. It's warmed up by an external flame. The contents of the cylinder expand. It does work on the surroundings. It pushes the piston outward against the external pressure. If our system absorbs 559 joules of heat and does 488 joules of work, what is our value of delta E? So our change in energy is our heat plus our work. So think about, what's our heat? Is it positive or negative? What's our work? Is it positive or negative? All right, which of these two numbers is going to be our heat? Yeah, 559 is our heat. We've got 559 joules of heat, and we've got 488 joules of work. The 559 joules of heat, was that added? Was that gained by the system, or was that lost by the system? It was gained, right, because it says absorbs. Gained by system. So our Q value is a positive number. And then our work value, is that a positive number or a negative number? It's negative. So our system does 488 joules of work. So our system used 488 joules of energy to do the work. So that makes it a negative number. Just like if you go out and do a bunch of work, you lose energy. You're not energized usually by doing work. So our equation, we've got our 559 joules minus 488 joules. So our total change in energy is like 71 joules. Yeah, 71 joules. And that's a positive value. So our system overall gained 71 joules of energy. Questions about heat or work? Okay, so again, we've mentioned heat is a transfer of thermal energy. It's one of the ways that we can move energy, and we're transferring thermal energy, hot and cold. And it goes between the system, whatever the thing that we care about is, and everything else, the surroundings, and that's caused by a difference in temperature. Temperature is our measure of thermal energy within a sample of matter. Strictly speaking, it's not a transfer, but the way that we measure things, we always have to transfer a little bit of heat to figure out what the temperature is. Heat is going to flow from the matter, the object, the things with high temperature, to the matter, the object, the things with low temperature, until they reach the same temperature. At thermal equilibrium, temperature does not change. There is still some exchange of energy going on just because of the molecules, the particles bumping into each other, but the temperature values are not going to change. So think of if you take a big cup of cold water or warm water, you add a couple of ice cubes to it, you shake it around, you swirl it around. Over time, the energy between the water and the ice is going to melt. Once the ice is all melted, the whole mixture will all come to the same temperature. The same thing will happen if you've got an excess of ice. It'll all eventually settle out at one final temperature, and then you've got a nice, smooth, consistent temperature throughout. If you add the ice right away and you take a sip, your water's probably still going to be a little bit warm. You might get little tingles of the cold sensation from the ice, but there's still heat transfer going on. Once the ice is all melted, everything's settled down, then your temperature is not going to change anymore. When a system absorbs heat, when it gains heat, positive Q, its temperature increases by some amount, some change, delta, in temperature T. This amount is proportional to the amount of heat absorbed. There's a proportionality constant that we call heat capacity, which has the value of C, or the symbol C. And the heat capacity has units of joules per degree Celsius, I'm getting ahead of myself, or joules per Kelvin. The reason that it can be degrees Celsius or Kelvin is because Celsius, degrees Celsius, and Kelvin are the same size unit. The only difference between degrees Celsius and Kelvin is that one of them is shifted relative to the other. So our Kelvin sets our floor at 0. Degrees Celsius, 0 is up at like 273 Kelvin. So it's just a shifted version, but the unit size is actually the same. A change in 1 degree Celsius is the same as a change in 1 Kelvin. So that works because we're using a change in temperature. We typically are not going to be using heat capacity. And the reason for that is what we'll see here. So the issue with heat capacity is that the larger the heat capacity, no, that's not it. The bigger the object, a large object is probably going to have a bigger heat capacity than a small object because it depends on the amount of matter. So notice that there's no specification. It's just energy and degrees Celsius. There's no specification for the size of the object. So if I take a big lump of metal and a little, like a coin or something, and I measure the heat capacity, even if they're made of the same material, the big object is going to have the higher heat capacity just because it's bigger versus the small object. So heat capacity is an extensive property. It depends on the amount of stuff we have. Depends on amount. Which makes it generally not a particularly useful or used, at least in general chemistry, it makes it not particularly used that much because of it being an extensive property. We are more often going to be using specific heat capacity, which has usually some sort of a subscript. It's also sometimes lowercase c. Usually if you see C as the symbol, we're talking about specific heat capacity. The specific part of specific heat capacity is 1 gram. So we're specifying 1 gram. And since we're talking about 1 gram of the material, if we have a small amount of the material versus a large amount of the material, that per 1 gram part accounts for the difference in amount of material. We also have a related property, molar heat capacity. So this is the per mole version. These are both intensive properties because they account for the amount of stuff. They don't depend on amount. So for example, 5 grams of copper has the same specific heat capacity as 500 kilograms of copper, because it's on a per gram basis. So it's scaled to the amount. If we were talking about just the heat capacity, it's probably fairly obvious that 500 kilograms of material is going to take a lot more heat to change temperature than 5 grams of that same material. So they'll have different heat capacities, but the specific heat capacity will be the same because it's the same material. Usually we are going to be using specific heat capacity, and our equation for specific heat capacity is Q equals mc delta T, where our C value is our specific heat capacity and it's got units of joules per gram degree Celsius. We could also use joules per gram degree Kelvin, again because our Kelvin and our degree Celsius are the same size unit and we're using a change. This change in temperature is going to be our final temperature minus our initial temperature, and these are quantities, the C values are quantities that you would look up, like in a table 7.4 here. Usually for metals, the values are pretty low. So notice we've got for our elements here, these are all metals. They're all below 1. For some other materials, like water's got a really high specific heat capacity of 4. Other things are going to have higher heat capacities. Typically, though, metals are below 1. So water's cool. Water's neat. It can absorb a lot of heat energy because of this really high specific heat capacity. And so if you're by the coast, particularly if you're in an area where the water is cool, like on the West Coast where we are, if you go to the beach, the water is going to be really cool because the water is cold and it's got a high heat capacity. It can absorb a lot of the extra energy from the surrounding area. So for example, San Francisco might be 68 degrees in the heat of the summer, and Fresno would be 100 degrees Fahrenheit because we've got mostly dry land that doesn't absorb heat well. So water is often used as a coolant. They're using too much of it for cooling AI data centers, which is so cool, so neat. But that's one of the reasons that it's often used, is because of the high heat capacity. It's also used in like your radiator to keep your engine cool if you're driving a car, often combined with other things so that it doesn't boil over. All right, let's do an example. So heat capacity can be used as one tool. Specific heat capacity can be used as one tool to identify materials, just like we can also use density. I think we did a density of like a platinum ring as an example. We can do a similar thing with specific heat capacity. So let's say that we find a shiny gold-colored rock. We want to figure out if it's actually gold. So we want to measure its specific heat capacity. So our chemist, our student, weighs the rock and finds that it has a mass of 4.7 grams. And then by transferring some heat and measuring that heat, probably with some water, the student finds 57.2 joules of energy into the rock, correlates with a change in temperature from 25 degrees Celsius to 57 degrees Celsius. So we want to find the specific heat capacity of the thing that's in the rock and see if that's consistent with it being gold, which would be so cool. So we've got our equation Q equals mc delta T, also sometimes called MCAT, because delta kind of looks like an A. We are trying to find specific heat capacity C. So we'll divide both sides by m delta T to move those over. flip it left and right so that it's a little easier to plug numbers in. Q over M delta T. So our 57.2 joules divided by our mass, 4.7 grams, and also our change in temperature, 32 degrees Celsius. The units that come out is just all the units. We didn't cancel anything out, so it's joules per gram degree Celsius. And the value that we get is 0.380, somewhere in there, joules per gram degree Celsius. Relatively simple algebra, math. So then we would just have to go consult a table, so I'll go flip back to that now. If we look at our table, gold has a value of 0.128 versus the 0.380 that we found. What do we think? Is it pure gold? Probably not pure gold. Almost definitely not pure gold. Could there be a little bit of gold in there? Maybe. But it's definitely not pure gold, so we're missing out on our big payday. Let's say that a 55-gram aluminum block absorbs some heat. Please find the final temperature of the aluminum. I'm going to jump back and grab our C value. 0.903. Let's go ahead and give that a try. All right. We've got relatively simple in terms of like there's not a lot of reading into it that we have to do. Relatively simple problem for heat capacity and temperature change. So we're told that it's a 55-gram block of aluminum. So 55.0 grams is going to be our mass. The aluminum identity here is how we knew to go and grab the correct specific heat capacity value. These are numbers that you would be given on an exam. The only one that you might be expected to know, but probably not, would be the one for water, which is 4.184. It depends on the temperature, though. It's initially at 27.5 degrees Celsius, so that's our initial temperature, TI, 27.5 degrees Celsius, and it absorbs 725 joules of heat. There is a potentially, there is one place where this could become tricky, is if instead of saying absorbed or absorbs that much heat, it could say that it loses that much heat. So what this word absorbs is letting us know is that heat is gained by the aluminum. So it's going to be a positive Q value. That's kind of all that it's telling us there. So if we've got an aluminum block and it's absorbing heat, what do we expect to happen to the temperature? Is the temperature going to go up or is the temperature going to go down? Temperature is going to go up. Part of the reason that I ask this question may feel fairly obvious. Part of the reason I ask the question is because it's possible that we could do this wrong. We get a smaller temperature value than our initial, and then that would be a signal to us we screwed something up. So we're expecting to see our temperature be bigger, our final temperature. So Q equals M C delta T, where delta T we expect to be positive. It's TF minus TI. So plugging in numbers, because I know that some people like to just plug numbers in right away. We've got most of the numbers, but we don't have delta T. So we're going to have to find delta T. So we'll divide both sides by 55 grams and also by 0.903 joules per gram degree Celsius. You could also choose to do that before you divide both sides, which would be less writing, maybe. Okay, so that all that stuff on the right side cancels out, and we get our delta T, 725 divided by 55, also divided by 0.903. We get 14.597 equals delta T. Now, if you weren't paying attention, if you didn't write everything down, it's possible that you would just get this temperature value. This would have degrees Celsius with it. It's possible you would get this temperature value and say, that's my final answer. And that's a case where it would be helpful to think about our temperature is supposed to go up. If this is our final temperature, that's lower than our 27.5 degrees Celsius. So 14.597 and change cannot be our final answer. That's our delta T. Our delta T is TF minus TI. And we know what our initial temperature was. It was 27.5 degrees Celsius. So 14.597 and change degrees Celsius equals TF minus a weird 27.5. Our final temperature is our initial temperature plus our change in temperature. So our final temperature is actually 42.1 degrees Celsius, which is bigger than our initial temperature, so that fits with what we were expecting. So we probably didn't screw up too bad if we did screw up. Questions? Cool, we'll run through a couple more slides. Or, no, we'll stop there.